2 minutes more, okay? No problem.
Yeah.
Remember when you and I were in school, Henry, it was just chalk and a chalkboard? Times have changed. Okay, I can hear the bell outside, so it must be time. So we have a guest here today. This is Henry from Academic Student Support. So he's got some great things to tell you, so I'll just turn the time over to him here to start with.
I'm with the Academic Support Center. We're located in the Student Union building across from Stingers. We provide tutoring in a variety of classes. Some of the new stuff we tutor is your kinesiology classes. So if you're struggling with the material and you want some help, come over. If the tutor that handles kinesiology isn't there, they can tell you what time they're there and help you set up an appointment. We also have writing tutors. Do they have to write papers in here?
Not so much in this class, just essays. So yeah, essay help would be great.
So if you want help with an essay, come over. The writing tutors can help with that. We have math tutors if you're struggling in a math class. I tutor chemistry and physics. We also have biology tutors. So really, most of the classes, especially freshman, sophomore, that you need help with, you can get help with. Hours are 9 to 4. We do have study halls from 5 to 8, Monday, Tuesday, and Wednesday.
What building are you in, Henry?
The Student Union building.
Okay. All right.
Any questions? Okay.
Okay. Well, I appreciate you coming.
Thanks for the time.
Sure.
Thank you.
Okay, gang. Well, I have a few links to load for some application stuff, so I'll just load those up and then we will start. So first exam is next Wednesday. So I'll be posting a study guide probably by Wednesday this week, so you have a week to kind of look over that. Number one. So the exam will just cover chapters 1 and 2, so we will get into chapter 3 Wednesday and Monday, but won't be on this exam. One more. All right, shut the door. Go. car starting. Car was barely started this morning, so happy. Okay, so we'll have our first exam next Wednesday. Study guide posted, there'll be a separate folder for that. So pay attention to that. Any questions? Pay attention to the study guide, PowerPoints, textbook chapters, all those things. Come to office hours. Email, I check email several times a day, so just prepare yourself. Try to take a few minutes every day leading up to the exam and doing something to prepare, so you'll get a better score. So my goal for today is to finish off Chapter 2. So Chapter 2, linear kinematics. What's the difference between distance and displacement? Distance versus displacement. So the question is how far? So we have potentially two ways to answer that question of how far.
Distance is like how far it actually went, but then displacement is like where you end up, kind of.
Yes, that's very good. So the distance is the total length of the path traveled by a body or object, and so that's a scalar quantity. Excuse me. Whereas displacement is a vector. So in addition to how far, what else do we want to know?
Start and finish.
Yes. So vector means what?
Magnitude.
Magnitude
Direction.
and
Direction.
yes, direction. Okay. So displacement and distance defined as the change in position. What variables are defined as the rate of change in position? Rate of change in position. So we're considering the time component.
Velocity.
Yeah, velocity and
Acceleration.
it's not there yet. Keep that. Yeah, speed, velocity and speed. So a good test question might be displacement is to velocity as something is to speed. Remember those types of questions? Yeah, distance is to speed. So speed is distance divided by time. Velocity is displacement divided by time. So then we're building on that. So velocity and speed, the rate of change in position. So as Haley mentioned, acceleration, so that's the rate of change in velocity. So how do we calculate average velocity over a time interval? So at any given period of time, the change in velocity is equal to what variables do we want to consider?
Displacement. Time.
Yes, so we want to consider velocity. So final velocity
And initial velocity.
and the initial velocity, we compare those two divided by the time interval over which the change in velocity is taking place. So if we have no change in velocity, what is acceleration equal to? 0, because velocity is constant, right? So what is the uniform acceleration of a projectile? What's that number? We just barely used it in lab.
-9.81.
Yes, negative 9.81 meters per second squared. So can a human body be a projectile? Yeah. So a human body can have, when we jump, can have a certain trajectory, can have a certain horizontal displacement, can have a certain vertical displacement, can have a vertical velocity and a horizontal velocity, so we can get those different components. So a projectile will speed up, will slow down in the positive direction. Okay, slowing down in the positive direction gives us negative acceleration, until which point we reach the peak of flight, and then we begin to speed up in the negative direction. So speeding up negative direction is still negative acceleration. So because we know that ignoring air resistance, acceleration is the same during the time which an object or body is in the air, we can predict certain things like how high or how far an object will travel, what the velocity will be at any given time point, So this is something that you'll have on the exam. These are our projectile equations. Because gravity only affects the vertical component, the projectile equations apply to vertical application of projectile motion. So we still have horizontal velocity and displacement. So in that case, horizontal displacement is equal to the horizontal velocity, denoted here with the x, multiplied by the time. Okay? Whereas everything here, as you can see, denotes the vertical component. So if we're trying to jump as far as possible, then we're going to have both a vertical and a horizontal takeoff velocity. So we'll have those two components. So we want to stay in the air long enough to get the maximum amount of horizontal displacement. So we'll watch a video on the long jump today that talks about takeoff angle and takeoff velocity and how important those things are to performance. But the reason this table is so nice, and you'll have it for the exam, so please don't stress about memorizing equations. You do need to know how to solve equations, is if you have unknown variables in these columns, so unknown variable, if you want to find this, so you look for the one you want to find, and then if you have different combinations of known variables. So typically with a problem, you're given a couple of variables. So with a problem, you want to write down what you know to start with, like mass or initial velocity or final velocity or initial vertical position. You write down what you know, and then you look at, okay, well, what do I want to solve for and what do I have? And then you can choose one of these equations to get what you are trying to solve for. So today we have, as usual, practice problems, okay, to get you ready for the exam. So I would highly suggest you go through these, try to participate, because it's exactly what you're going to be doing on the exam. So it's a good study tool. Okay, so we talked about acceleration due to gravity. So if an object or body is in free fall, we know that initial velocity is 0. So then we can use this equation right here. So if initial velocity is 0, then pretty much we're just looking at this part of the equation. And so if initial velocity is 0, then we can solve for vertical position at any time point throughout that period of free fall. And so then you would just be looking for the time interval. We know what lowercase g is negative 9.81 meters per second squared. So then it becomes relatively easy to solve for the final position at any given time point. So here you have the vertical position as well as the vertical velocity at 4 different time points: 1 second, 2 seconds, 3 seconds, 4 seconds during a period that an object is in free fall. And so we just use this equation because the initial vertical velocity would be 0. That's before we drop something. So how many of you have seen this sport in the Olympics? Okay, it's been around since the 2000 Olympics in Sydney. Pretty exciting. So how many of you had one of these in your backyard as a kid? I've got one for my 4 kids. They're a lot safer now than they used to be. So we have this nice reinforced net all the way around, and there's recommendations about not putting too many kids on there at the same time. Whereas back in the 80s, we had like 10 kids, no net, and we all survived. A few bumps and bruises. A trampolinist springs vertically upward with an initial velocity of 12 meters per second. So that's your initial vertical velocity. So how high? So in this case, you'd be looking for the change in vertical position relative to the surface of the trampoline. So in this case, we're not given how high the surface of the trampoline is off the ground. We're just considering the surface of the trampoline to be the initial vertical height. So in this case, y would represent the final vertical position. How high above the trampoline surface will the trampolinist go given an initial vertical velocity of 12 meters per second? So you could hypothesize that the faster the initial vertical velocity, the higher the individual would travel, ignoring air resistance and independent of mass. So you take two people that have different masses, as long as their vertical velocity upon leaving that surface is the same, they're going to go the same height. And of course, ignoring air resistance. So what I'd like you to do is solve for y. And so what we could say is initial vertical velocity is 12 meters per second. So when this trampolinist reaches the peak of their flight, in other words, the final position where they're not going up anymore, what's the final vertical velocity going to be? 0. They're not going up anymore. So final vertical velocity is equal to 0 because we're looking for peak height when they have stopped going up, just before they start to come back down. So final vertical velocity is equal to 0. Initial vertical velocity is 12 meters per second, so you have to square that number, and then you're adding 2 multiplied by g. Okay, so what's g equal to? You're right.
9.81.
Positive or negative?
Negative.
Negative. So I will let you know, there was a problem in lab today where we actually used positive just because the way the math is, but unless I tell you, always just go with the negative 9.81 meters per second squared. So 2 times negative 9.81 meters per second squared multiplied by what you're solving for would be the final vertical position. So you're going to end up bringing the 12 meters per second squared over to the other side of the equation, right? And then dividing that by what? Just using your algebra. 2g, because you're solving for what? Just the position, right? So what's 12 squared? 144 meters squared over second squared, right? Because you're squaring meters per second too, so 144 meters squared over second squared. So we need to bring that over to this side of the equation. You've already got rid of the VF squared because that's 0. So if you bring 144 over to the other side, it's negative 144. What's 2 times g?
19.62.
Positive or negative?
Negative.
Negative 19.62. So it ends up being negative 144 divided by negative 19.62, right? And so if you cancel all the m's and the s's, you end up with how many m's left? Just 1, because that's your final vertical position in meters. So if this individual leaves that trampoline surface with 12 meters per second vertical velocity, how high is she going to go? In meters. So in other words, what's your answer? Negative 144 divided by negative 19.62 is equal to what? 7.34 meters. So is that over 20 feet? Yeah. Pretty high. God, I don't think I'll ever try that, but yeah, pretty high. Does everybody understand this one? Does everybody understand why final velocity is equal to 0? Okay, so we're good to keep going? Okay. Okay, so parabolic trajectory. How many of you have heard of that term, parabola? A parabola characterizes a projectile that has both vertical and horizontal components, right? So from your textbook, this is a figure that shows tossing a ball that has both vertical velocity and horizontal velocity. So you can pretty much tell whether a ball is going to go really high or really far based on the initial velocities, right? So if you have a really high vertical velocity and a lower horizontal velocity, the ball's going to go up more than it is going to go out. So conversely, if you have a really high horizontal velocity and not so much vertical velocity, it's going to go really far, but not very high. So the velocity can tell us the release velocity, the horizontal and vertical components can really tell us a lot about what a projectile is going to do. In fact, if we ignore air resistance, and we get to ignore air resistance all the way up to chapter 8, so we just ignore it until then, and yes, it's important, but if we ignore it until then, we can predict how high and how far an object will travel based on the conditions at release, because we know that gravitational acceleration is constant. So if we have all the numbers we need, what's the initial vertical, what's the initial horizontal velocities, what's the initial vertical position, we can determine before the ball even lands, mathematically we can tell how high it's going to go and how far it's going to go because we know about gravity. So the immediate application would be a long jump, right? So that's your classic parabolic trajectory going up and then coming down. So in theory, to jump as far as possible, you'd want a takeoff angle of about 45 degrees, right? So in practice, though, that's actually not true. So they find elite long jumpers have takeoff angles much lower than that, somewhere around 18 degrees. So they figure the trade-off is that with a smaller takeoff angle, athletes are able to generate a higher takeoff velocity. So what is true in theory is not always true in practice. So we see different trajectories for a high jump where we want just enough horizontal displacement, but not too much. So you want to go as high as possible, but you still have to get over the bar, which is horizontal. Basketball shot, a ball has a greater chance of going in if it has a good arch on it. And then a hammer throw. So as we discussed on Thursday, if we ignore air resistance, the horizontal velocity will be constant all the way through the flight because gravity has no effect on the horizontal. Air resistance does, but again, we haven't got to that yet. So what do you notice about vertical velocity? Gradually gets smaller, right? So an object, or in this case a hammer, would be slowing down in the positive direction until it has no vertical velocity at all and then starts to come down. So an object is either going up or coming down. There's no in the middle. So again, ignoring air resistance, this hammer would be going up for exactly half of its flight, and it would be coming back down for exactly half of its flight. So objects or bodies, humans included, are either going up or coming back down. So there's no in the middle. So your hang time, as they say, would be the total time from takeoff to touching back down on the ground. So what's really good? So some of the best leapers, old video recordings have been analyzed. The best leapers on the planet can be in the air for about 1 second, is elite. So if you're in the air for 1 second, how much of that second is spent going up? 0.5. So you spend half a second going up, half a second coming back down. So it looks longer, doesn't it? Like you see some of those Dr. J, dunking, seems like from the 3-point line, but No, it's about 1 second. The best leapers can be in the air. Okay, so speaking of which, Isaac is attempting to high jump over a crossbar set at 2.13 meters. So that's 7 feet. Good high jumper. At the instant of takeoff, when he is no longer in contact with the ground, his vertical velocity is 4 meters per second, and his center of gravity is 1.25 meters high. So what's center of gravity? What does that mean? The center of gravity of an object or body, what is that? The middle, yes, that's a good way to think of it. Maybe the balance point. Can our center of gravity change? So I'm in the anatomical position, right? Remember this from way back? Okay, so then what if I move my arm over here? What happens to my center of gravity? Yeah, it moves that way. So the center of gravity moves according to where you have the greatest concentration of mass. So if I do this, where does my center of gravity go? It goes up a little bit. Okay, so center of gravity in the anatomical position is about 57% of your standing height. So about the umbilicus is where it's at. But that can change. It can be inside the body. It can be outside the body. How many of you knew that when a high jumper clears a crossbar, their center of gravity can actually be underneath the bar? So how is that possible? You think, okay, well, my center of gravity has to at least go over the bar, but how is their body positioned as they're going over a bar? Is bent in half. Yeah, that's a good way to describe it. So actually, if you consider both halves of their body, and if they're close enough to the bar, the center of gravity can actually be underneath the bar because they've got portions of their mass distributed on either side. So that's interesting. But you think, okay, so center of gravity, if you think it's a good jump, they're good at positioning their body to get over that bar, their center of gravity is going to have to go from 1.25 when they leave the ground, at least maybe a little bit more, or at least equal to 2.13. So this is where their center of gravity is when they leave the ground. So they're starting their jump. Their jump leg has just left the ground, and their center of gravity or center of mass is 1.25 meters. And they've got to move their center of mass over this bar, or at least close to it, which is at 2.13 meters. So the velocity at takeoff is really important. And I'm sure, I don't know much about high jumping, but I'm sure there's a lot of technique involved in actually being able to, once you're up there high enough, to actually successfully get over the bar. So, a couple equations to solve for. So, how much time elapses after takeoff until Isaac reaches his peak height? How much time? So, we could use this equation right here, because at his peak height, what is the final velocity going to be? 0, right? Do we know what initial velocity is? Yeah, we were given that, 4 meters per second. So that's how fast he's moving at the moment of takeoff. His center of mass is moving vertically 4 meters per second. So let's see if it's enough to get him over the bar. So G, negative 9.81 meters per second squared. And all we're left with is time. So that's what we want to know. How much time elapses after takeoff until Isaac reaches his peak height? So we're looking for the first half of that flight. So if we know what the time is for the first half, can we estimate what the time will be for the second half? Yeah, because time up is equal to time down. We don't really need to know that, but we're just looking for the time to get to the peak. So I want you to take this equation and solve for time. Knowing that initial velocity is 4 meters per second, knowing final velocity is 0 meters deeper, it's gonna be in the air for 0.82 seconds, right? Considering the up and the down. We only need to know what the time up is to eventually solve for the vertical position. So does everybody understand that? So we had 4 meters per second, we brought it over to this side, and then we had negative 9.81. We divided both sides by that. So you had negative 4 meters per second divided by negative 9.81, and you should come up with 0.41 seconds. Okay. All right, so now the critical question. Has Isaac generated enough vertical velocity to get over the bar? So what peak height does Isaac's center of gravity achieve? So we're hoping it's right around there, otherwise he's not going to get over the bar. So we're going to use this equation right here. And you're going to solve for YF, the final vertical position. So do we know what the initial vertical position is of the center of gravity? Yeah, we were given that, 1.25 meters. So I would suggest that you have all three components of this equation, so yi, and then you have this second component here, vi times time, so 4 meters per second times, what was the time? 0.41, that's the second component, and then you're going to have a third component over here. You're going to end up subtracting this third component. Can anyone tell me why? Because the g is negative, right? So you're actually going to end up subtracting this part from the first two that are added together. So 1/2.
We're still using 0.41 for all of them.
Yes. Yep. Because we're only considering to go from the takeoff to where he's at his peak height. So it's 0.41 seconds in both cases. You'll square it over here. So you got the first two components, you'll add those together, and then you'll subtract whatever you get here, and you'll subtract because g is negative 9.81 meters per second squared. So my question to you is, has he got enough velocity to get over the bar? There you go, good. No, he does not. He's not going to make it. So he should be coming up with something like 2.07 meters. He's up there quite high, but he's not going to get over that 2.13. Probably going to run into the bar and then land on the mat. So is everybody okay with how we got that one? 2.07 meters. Okay, so how's Mr. Isaac going to get his vertical velocity to be higher? We go on, right? We need to do some type of lifting that mimics the motion of takeoff, that improves his takeoff velocity by increasing his rate of force production into the ground. And so Isaac embarks on this mission to get over 7 feet. So after 6 months of resistance training using Olympic weightlifting movements, Isaac's takeoff velocity increases to 4.7 meters per second. So now rather than taking off with 4 meters per second, he's added almost 1 meter per second onto that. What peak height does his center of gravity achieve? So you need to take that new initial vertical velocity and solve for A and solve for B. Again, because his time to go up is going to be higher because he's starting out with a higher velocity from the ground. As soon as his foot leaves the ground and he starts to go up, is he slowing down or speeding up? No longer in contact with the ground. As soon as he's no longer in contact with the ground, he's immediately going to start slowing down until at the top his vertical velocity is 0. So if he's putting more force into the ground at a faster rate, and his takeoff is now 4.7 meters per second, his time to reach his peak height will be longer. And then his center of gravity will also go higher. So is he a 7-foot high jumper now? Anybody got the time part solved? What's his time?
I got 1.5.
Well, he's a leaper now. So 0.47. That ought to be enough to get him over that bar. How many meters is he getting to with his center of gravity? Did he clear it? What do you think? What'd you guys get? Everybody get that? 2.375? So he's got room to spare getting over that bar. Okay, so questions? Okay, so got a little video clip here for you. It's about 3 minutes. Before we watch that, I want to talk a little bit about this related concept. So in this video, they're going to give you some numbers. And what I would like to do is calculate rate of force development So anytime we have a rate, like the rate of change in position or the rate of change in velocity, what are we considering? It's not just
over time.
how much, but this quantity, good Courtney, is relative to time. So under normal circumstances, it takes a trained person a little less than a second to go from zero force to maximal force in absolute terms. So zero to all the force their muscles can generate in a little less than a second. So that's the absolute amount of force. How long is a sprinter's foot in contact with the ground during each stride? It's about 1/10 of a second. So you look at things from different perspectives. You go, okay, well, it takes muscles maybe 0.8 of a second to go from zero to max. But you have a sprinter who is putting force into the ground in about 1/10 of a second. So what fraction of their maximal strength can they really use? So this is really, really important. So being able to use a bigger fraction of your maximal strength. In other words, this is what we could say is usable strength, right? That's the amount you can use because you have only 1/10 of a second. You don't have all day to generate your maximal amount of force. You just have a fraction. You're only going to be able to use a fraction of your available strength. So if you can somehow use more of the strength that you have, you're going to be better off because there's a relationship between how much force in a limited amount of time and velocity, right? So more force means more vertical and horizontal velocity at takeoff. So what I want you to see if you can catch how much force this high jumper puts into the ground in a given period of time, and we're going to calculate the rate of force development. Let's see, high jump. That's the one we want.
At 6 feet tall, Jesse Williams can jump 21 inches over his own height. A differential that helped him become the current world champion high jumper. To break down how he does it, we'll begin with technology.
What we want to do is we want to put an AM sensor on you. So this is basically an accelerometer, so it's going to tell us exactly how fast you're running up, and we'll also be able to calculate force numbers as you jump.
He converts his horizontal velocity into vertical height by generating power. Because power is a result of force over time, the less time it takes Williams to launch, the more power he can potentially produce.
Unbelievable.
Williams' launch foot is in contact with the ground for only 133 milliseconds.
Okay, write that down. What was it? 133 milliseconds?
And generates about 1,200 pounds of force.
There you go, right there. So that's with one leg. That's with his jump foot. So 1,200 pounds into the ground over a time interval of 0.133 seconds. So what's his rate of force development? In other words, pounds per second is our newtons. Even though the force plate that we have downstairs is newtons per second, let's just, for the practical application here, pounds per second. 1,200 divided by 0.133 gives us how many pounds per second? It's going to be a big number. What was it?
9,022.
Yeah, 9,022 pounds per second. So it's not the person who is absolutely the strongest, it's the person that can use the most of their strength in a fraction of the time that is going to jump high.
Which is roughly 8 times his own body weight.
8 Gs.
But the high jump isn't only about power, it's also about technique. During his launch, Williams rotates his torso at an optimum 300 degrees per second. Just a 20
angular
degree
velocity.
increase in his angular velocity would cause his body to over-rotate and hit the bar. And strangely, even though Williams' body goes over the bar, his center of mass stays under it. This phenomenon occurs because his back is arched at about 140 degrees during the peak of his flight, placing his center of mass technically outside his body. Since Williams is used to approaching and clearing a simple high bar, we decided to see if an unfamiliar challenge would affect his mental approach. We're gonna see if you can jump over me with my arms over my head. We'll see if I can pull it off. Here we go. 3, 2, 1, go. Oh my God! From the ground to the tip of my fingers measures 7 feet 3 inches. That's higher than an average door frame. Jesse Williams can actually jump a lot higher than even my standing reach. Last year, he cleared 7 feet 9 1/4 inches. That's like jumping over Yao Ming on his tippy toes. For ESPN Sports Science.
Okay, that was kind of fun. Unbelievable. Got superheroes on this planet. Okay. Let's talk about football, right? Hopefully the teams that you wanted to won yesterday. So football is punted into the air. It has an initial vertical velocity of 15 meters per second. So it's also going to have some horizontal velocity because it has to go downfield, but it's going to have a certain height that is associated with the vertical component of its initial velocity. So when it leaves the kicker's foot, if the ball experiences a constant vertical acceleration of negative 9.81 meters per second squared while it is in the air, what is its vertical velocity 2 seconds after it leaves the kicker's foot? So let's take a look. This is probably the easiest equation. So we're given pretty much everything we need. So we have an initial vertical velocity of 15. We know what g is. We know what t is, right? So we're looking for the vertical velocity 2 seconds after it leaves the kicker's foot. So 15 meters per second plus, and then negative 9.81 meters per second squared. So this component is actually, you're going to end up subtracting it. So you want to take negative 9.81 meters per second squared multiplied by 2 seconds before you subtract it from 15. So let me ask you a question about this problem. Is the ball still going up, or has the ball reached its peak and started to come back down? And how can you tell based on your answer? It's starting to come back down. How can you tell? Yeah, so your answer, the final velocity, 2 seconds after it leaves the kicker's foot, is negative 4.62 meters per second. So it's cleared the peak, and now it's started to come back down and is traveling downward with a velocity of 4.62 meters per second. So does that make sense? We good on that? Okay, this is Ray Guy. He was a Hall of Fame punter. He actually passed away in 2014, but he's ranked one of the 15 greatest punters of all time. So I thought I'd throw that up there. Okay, so if you were watching a basketball game from maybe a view that a drone would have or from an overview, you would notice something if you could slow down the motion of a ball during a free throw, that the horizontal motion of a projectile is constant, ignoring air resistance. So for every unit of time, the horizontal displacement of the ball is going to be equal. So it's not like, remember the previous example where we dropped something and that object is in free fall? So for every second of time, that object is in free fall, its vertical position is it the same or is it changing? It's changing because it's acceleration, right? It's accelerating downward at a rate of negative 9.81. So horizontally, ignoring air resistance, which for the most part indoors we can do that, for every unit of time, the horizontal displacement is going to be the same. So to solve for horizontal displacement, you just rearrange the velocity equals displacement over time, and you just take velocity multiplied by time to get the displacement. But for every fraction of time, the displacement would be exactly the same. Okay, so Carl leaves the long jump takeoff board with a vertical velocity of 4 meters per second and a horizontal velocity of 9 meters per second. So long jumper, we have a high-speed camera, and we're able to calculate at takeoff the vertical and horizontal component of their velocity. So horizontal makes sense, right? So you can see based on these numbers, he's got a little bit of upward velocity, but mostly horizontal. So why does that make sense for the long jump? How well would you do in the long jump if it was 9 vertical and 4 horizontal? Not very well, right? So we want out, but we want just enough up that the time in the air is enough that we can get the most out of our horizontal displacement. So pretty easy. There's really not much calculating involved here. So what is Carl's horizontal velocity just before he lands, ignoring air resistance? Yeah, it's going to be 9 because gravity doesn't affect the horizontal component. Okay, so let's go down to C first, and then we'll come back to B. So what is Carl's vertical velocity the instant before he lands should be his during his 0.85 second flight? So the height of takeoff is the same as the height of landing. So if the vertical velocity at takeoff was positive 4 meters per second, and the height of landing is exactly the same, so at the instant of landing, what should it be knowing the uniform acceleration of gravity? Negative 4 meters per second. So rather than going up, now coming back down at the same height, the velocities are going to be the same vertically except in opposite directions. And again, that's just because of the uniform gravitational acceleration. So let's do this middle one here. So if Carl is in the air for 0.85 seconds, what is the horizontal displacement during this time in the air? So now you're using your horizontal equation. So we have 9 meters per second is the horizontal velocity multiplied by 0.85. So rearranging this equation to solve for D, horizontal displacement. So we're just bringing the T up here. So the time is 0.85 multiplied by the horizontal velocity of 9. So what'd you get in meters for the horizontal displacement? Yeah, 7.65 meters, which, I don't know, convert that to feet. 25 feet, something like that, 25 feet. Pretty good leap for Carl. Okay, so this next clip is going to give us some science of the long jump.
For the past 4 years, Brian Clay has held the title World's Greatest Athlete. It's an award bestowed upon the Olympic gold medalist in the decathlon, a competition consisting of 10 track and field events held over 2 days.
On the first day, we do the 100 meters, the long jump, the shot put, the high jump, the 400. The second day, we do the 110 hurdles, the discus, the pole vault, the javelin, and the 1500.
While Clay ultimately failed to qualify for the 2012 Games in London, he used advanced technology to prepare for the long jump, one of the decathlon's most technically challenging events because it requires the athlete to sprint down the runway and launch himself at the exact moment that he reaches the takeoff board.
That's where the difficulty lies, is learning how to come in with somewhat of a rhythmic run up and then hit the board with as much accuracy as possible, and then of course catapult yourself and jump as far as you can in the sand.
When a person jumps to try to go far, they are becoming a projectile. So the human body is functioning as a projectile.
The mechanics of projectile motion are critical to Clay's performance in the long jump. Clay's velocity has two components: horizontal velocity, his sprinting speed, represented by X, and vertical velocity, his liftoff speed, represented by Y. From the time he leaves the ground, gravity pulls Clay down, changing his vertical velocity, but not his horizontal velocity, causing him to follow a parabolic path until he lands in the sandpit. Melvin Ramey, an engineer who has been supported by the National Science Foundation and a biomechanist for USA Track and Field, says that by measuring Clay's horizontal and vertical velocities, it's possible to find a crucial element of the jump, the takeoff angle, which will ultimately determine the length of the jump.
In general, world-class jumps are takeoff angles somewhere between 18 and 22 degrees.
In order to accurately measure it, Ramey and Clay are turning to an unlikely place for help. As part of a sponsorship package with the U.S. Olympic Committee, BMW is lending its engineering expertise by adapting a cutting-edge stereoscopic camera system to measure Clay's jump.
The BMW velocity system is using what we call a 3D camera or a stereoscopic camera. It actually has two lenses, and so it can triangulate everything that it sees in the field of view. They've made it recognize a template, and that template happens to be a white baseball hat.
As Clay sprints down the runway, the stereoscopic camera tracks the white cap on Clay's head, the most stable part of the body in motion, and takes pictures 60 times per second to calculate his horizontal and vertical velocities at takeoff.
What's the velocity here and the velocity here, the X velocity and the Y velocity?
This is Y, that's gonna be like how much you're going up.
Oh,
X
okay.
is gonna be
How
how
much
much you're
more
going
productive a
up.
practice
And
would
the
be if you
angle
could
is
have
gonna be
real time, like
your
those results?
velocity this way and your velocity this way.
Oh,
And
it's just-
we're able to
okay,
find
gotcha.
an angle between these two vectors.
Some cars are already loaded with cameras to provide drivers with feedback about what's around their car. But at the BMW Technology Office in Mountain View, California, Chris Pavlov is developing a future safety system that uses the stereoscopic cameras similar to those used on the track with Brian Clay, with specific computer software that calculates an object's distance from the car, such as a pedestrian crossing the street.
What we have here is a car that has depth perception. Current systems say, yes, there's a pedestrian. This can say, yes, there's a pedestrian, and it's 22.5 meters in front of the car.
While this stereo camera system is still in development for automobiles, the system at the Olympic Training Center has already provided valuable feedback to Clay and his coach.
With this technology, we actually will know how fast we're running, how much velocity we're maintaining off the board, and then we can actually do some calculations to see how far of a jump that should have been and how far of a jump it actually was. Yeah, it could be better. Still out a little bit.
Ramey says the BMW technology is useful because it provides real-time feedback.
This equipment gives it to us instantaneously. In other words, actually, while the athlete is in the air, we have already captured those velocities. So the advantage that we have now is that the coach can come and look at the performance immediately.
Now you can find the optimal takeoff angle.
Vital information for decathletes like Clay, who train and push themselves on the track 6 or 7 hours a day.
The more efficient we can be, the better off it's going to be for us because we have to save energy, we save time, we have more time to recover, less pounding on our body and our joints, which lead to less injuries. So all of that stuff can make a very big difference.
Okay, pretty awesome. So we got just a little bit more to go, so hang with me now. So chapter, we're talking about center of mass. So we refer to the center of mass as the overall balance point around which our total body mass is equally balanced and distributed. However, we also need to realize that our body consists of a series of segments. So each of those segments has its own center of mass. So all of these dots that you see here represent joints. And each of these segments will have the foot, the lower leg, the upper leg, the forearm, the hand, the upper arm, the head. All of these will have their own center of mass. And so that's what we can see here is when we make a free body diagram, we can define exactly where that center of mass is located for each of those segments. So, for example, the center of mass of each segment isn't necessarily through the exact center. So for someone's forearm, would you estimate the center of mass to be closer to the wrist or elbow? Yeah, closer to the elbow. Why? Because you got the mass of the forearm is closer to the elbow, right? So same thing with the lower leg. So the mass of your calf is closer to the knee joint. So it's going to be center of mass for that segment is going to be closer to the knee versus the ankle. So the overall center of mass of the body represents the summation of the center of mass for all of these segments together. So this represents the overall center of mass right here. So it can be inside or outside the body. It's very important. A few years ago, 15 years ago, I did this study back in Illinois, and we actually defined the center of mass for each body segment in calculating the volume of lifting. So volume of lifting is measured by taking sets times reps times weight. We took it one step further and actually calculated how much of their body mass they were lifting. So for example, with a squat, everything above your knee joints is part of that lift, right? Yeah, so you're not only lifting what's on your shoulders, but you're also lifting the mass of everything in your body in a squat motion for a given displacement, with the exception of everything below the knee. So the question, just in case, if you're curious, the question that we addressed in this study was looking at muscular endurance. So sustained contractions over a period of time. So we looked at failure versus non-failure. So over a period of 6 weeks, we had one group that did all of their sets right to exhaustion, right? How many of you have trained to failure where you can't do another repetition? Okay, that's failure. So and then we compared another group that did an equivalent amount of work or volume, but they weren't going to failure. So to equate those two, it was kind of tricky because we have to do more sets for the non-failure approach to equal the amount of work they were doing for the failure approach. Does that make sense? So ultimately they were doing the same amount of work. It was just fewer sets to failure versus more sets not to failure. So over the course of 6 weeks, they were doing exactly the same amount of work. It was just in one case failure, in the other case not failure. So it was a pretty good sample. We were using 15 rep max resistance, and you can see how strong these people were. So for the failure group, their 15 rep max was 120 kilograms. So that's rock bottom squat 15 times. That was their 15 RM. So they were, pretty strong people, 105 kilograms. So the randomization to each sample didn't quite come out perfect, especially with regard to the squat. It was a little closer for the leg curl, a little closer for the leg extension on their 15 RMs. What we ended up finding, here's endurance test 1, endurance test 2. For endurance test 2, the total amount of work, and we'll get to this in chapter 4, but work is expressed in joules. Joules, work is expressed in joules. So we found that pretty much they had the same amount of gain in joules for their endurance test. So the take-home message after all this measurement, after going in and actually calculating their body segment masses and how far they were lifting not only the weight but also their body mass, we found out that as long as you're doing an equivalent volume, you make about the same amount of gain in muscle endurance. That's a pretty good overall message. Can't believe that was 15 years ago. So last point of discussion for today. So from lab last week, looking at counter movement jump versus squat jump. So these figures represent a series of still frames. And if you look closely, you can see this pink dot that represents the center of mass. So during a counter movement jump. So a series of still frames that show the counter movement jump over time versus a squat jump. Remember in lab last week, you begin from this crouched position and then you take off. So you have this center of mass here. And so all through this chapter, we've been talking about these kinematic variables. And so we can look at a counter movement jump and a squat jump in terms of position, which is displacement, velocity, which is the rate of change in position, and acceleration, which is the rate of change in velocity. So let's take a look at position to start with. Counter movement jump versus squat jump. So these two lines track the position of the center of mass. So if we go back, this pink dot, so we're starting here, and then what's the first thing you do with the counter movement jump? It's that quick squat, right? That's what you see going on here. A series of still frames, the gradual squat, and then reversing it into the propulsion, leaving the ground, coming back down, landing, and then. So does everybody follow me on what's going on here? That's a counter movement jump. This is a squat jump, so there's no preload. It's just you're in that crouch position, and then what? And then you take off. So it's just propulsion. So tracking the center of mass. What shape does that center of mass make? Yeah, it's a parabola. That's the tracking the center of mass makes a parabola. So what we're doing here is just tracking that center of mass. The blue line is the counter movement jump. Pink line is the squat jump. This represents the position vertically of the center of mass. This represents the time of the jump in seconds. So notice with a counter movement jump, can you track the center of mass through the preload? The center of mass is dropping. And eventually you reach a point where the counter movement ends and what begins? You can see that upward propulsive phase until at point 0, that's when the feet leave the ground. So this time point right here, everything before the jump, everything during and after the jump. So at point 0, this is when the feet leave the ground. So does the center of mass still go up after the feet leave the ground? Yeah, it's going up. So you can see the jump right here in terms of just tracking the center of mass, coming back down, landing points right here, and then when you land, are you landing with your knees locked? I hope not. Okay, what happens when you land? Can you see that little dip? That's the knees bending and then standing back up. So this is what a motion capture system would give you, tracking that center of mass through two different types of jumps. Okay, now velocity. Okay, so can you tell me, question of the day, can you tell me what vertical velocity will be at the peak height of the jump? It'll be 0. Okay, so what I've done here is make a line. These three graphs line up. So can you see this would represent the peak height of the counter movement and squat jump? Which jump is slightly higher? Counter movement jump. We would expect that due to the preload. Okay, that's what you wrote your essay about. Okay, so this is the peak height, which corresponds with what vertical velocity? Velocity right here, 0 is right there. 0 velocity at the peak height of the jump. So it makes sense, right? So how would you compare the time up with the time down then? What did we learn today? It's equal. So we are going to spend a certain period of time going up, and then we're going to spend an equivalent period of time coming back down. As soon as the feet leave the ground, is velocity increasing or decreasing? As soon as your feet have left the ground on takeoff, what's happening to vertical velocity? It's shrinking, right? Till eventually it's equal to 0. Can you see how as soon as the feet leave the ground about right there, what's happening to velocity? It's shrinking down to what? So you have a certain velocity at takeoff, but then the velocity at the peak of your flight is equal to 0. So it's slowly reducing to 0. You reach the peak of your flight, then what happens? Come back down, right? Is velocity increasing or decreasing as you come back down? It's increasing. Okay, so now you have negative velocity, right? Until what point? Until you land right there. So velocity goes from 0 at the peak, and now you're coming back down. Velocity is a vector, so we have to define direction. So velocity is slowly increasing, but in the negative direction. Okay, so let's get to acceleration now. Acceleration. So this is acceleration over here. What's the acceleration during the time period of flight? Almost done. Negative 9.81 meters per second squared, right? It's right down here. What's this number right here on the acceleration? It's negative 10. So as soon as we get takeoff, as soon as our feet leave the ground, where does that acceleration go? It's right there, where it needs to be. So you can see the entire period of flight. This is the first half right here. This is the second half right here. But during that entire time period, the acceleration is equal to negative 9.81 meters per second squared until what point you land. Notice how high acceleration is on landing. So there's a proportionate relationship between acceleration and impact force. So if I was to, in the same article, they throw the impact force graph up there, it looks exactly the same as the acceleration graph. So if you replace this with force, where does your body experience the highest amount of force? Right there on impact. Okay, so we calculated some of that today. What's the impact force? How many G's of force are on your body for that moment of impact when you've hit the ground, no longer in the air? So do you have any questions on these graphs and how to read them? Okay, all right. Well, I appreciate everybody coming today. Have a great day. I'll see you on Wednesday to start chapter 3.